Hello, everyone. Welcome back to Physical Geology 1403. Before any of you ask, no, I do not moonlight at State Farm. This is just how my wardrobe ended up today. All right. I don't think about it that much. I just grab whatever pants are on top and whatever shirt's on top. And if it looks formal enough, if it's a collared shirt, I'm good. The matching, I don't really notice until someone says, "What's up, Jake?" I'm like, "Oh, oops." So, today is lecture 3. We're talking about igneous rocks and intrusive activity. Before we jump into that, anything anyone wants to ask me about? Any questions? In particular, any questions related to any large events that happened in the world? Where's my snake? My snake is currently tucked away under his log. I probably would have bothered to wake him up and bring him out today, except that I was running behind because of that meeting that I told you about. Yeah, so no snake right now. I might bring him out for lab if people really want him, but right now I'm just going to leave him be. We have a new president as of yesterday. Yes.
What do you think about that hill that Elon Musk popped?
About the what?
Twice.
Oh my god.
Elon Musk hit the Hitler salute twice.
Oh.
The entire room, no one was phased.
I forgot about that.
He hit the button twice.
Genuinely hit
multiple
that.
times.
Elon Musk is a character.
He did do that. That's insane.
Yeah, I greatly admire Elon Musk's imagination. I find myself more and more aghast at the things that he does. I obviously don't support or sustain such actions as Hitler salutes, but he's kind of, it's not a free pass, but that I'm giving him, but he's also the only guy that's really trying to push human civilization beyond where we are at the moment, whatever idiosyncrasies that comes with, whatever
Isn't he trying to make robots?
things. Yes, his Optimus robot is very promising. Missions to Mars, trying to get people back on the moon. All of these are things that I admire and I want to happen. Yeah, I strongly disagree with a lot of his personal statements and things. There's like a new story about Elon Musk every week. I don't know how many of you are gamers. Do you see the Path of Exile 2 shenanigans that he did?
Mm-hmm.
Yeah. He live streamed himself playing a game and said that it was his account. It's like a top 0.001% of the world account. And he live streamed himself playing it, and he clearly had no idea what he was doing. So it's pretty obvious to everyone that he paid someone to get him up there and then just took over his account so he could make everyone think he was a cool gamer. Anyways, so that's just how Elon Musk is, and I'm not excusing it, but I'm kind of used to it at this point. Anyways, all right, yeah, Elon Musk, good. Wherever you fall on the political spectrum, this yesterday was groundbreaking in many ways. New precedent set by the exiting president, and new precedent set by the incoming president. He signed, what was it, 200 executive orders on his first day. Previous record before that was 22. So he came out swinging. We'll see if he keeps swinging. Some of those orders had to do with climate policy. He withdrew us from the Paris Climate Accords, which are the last attempt that many nations in the world had to try and agree on a way for us to cut down on global warming emissions, things that contribute to global warming. We'll talk more about those emissions and contributions and things like that later on. But for now, let me just say that the United States completely pulling out of it is not, in my opinion, good. He did it to pave the way for things like increased oil production, which means lower gas prices, which means most people are going to support that decision. It's not a good long-term decision. but he's thinking about the next 4 years. He's not thinking about the next 40 or 400. So in a way, it's kind of understandable that he would choose to make that decision. But we'll talk about more of that, is more of the climate-related questions as time goes on in our class. It's going to be a different America today, starting today for the next 4 years, though. So buckle in, folks. It'll be interesting however you fall. Hello. Come on in. Okay. Any questions about anything we've discussed? Any earthquakes or volcanoes that you saw erupt over the weekend? There were a few. No?
No.
All right. Whenever there's a big natural disaster that happens during the week, I try and talk about it. None of the earthquakes that happened were really that. Like, there were a few 6.0s, nothing really major. But I will bring those up as they occur before our next class session. So, as always, please remember to ask your questions to me during class time. Don't be afraid to raise your hand. If you're not asking questions, then you're not doing science right. And I have no idea if you're even keeping up with what I'm talking about. Okay, so please ask your questions. Don't be afraid to interrupt me. All right, today we're talking about igneous rocks and intrusive activity. I'm going to start off with some quick drone footage here. What do you see? Describe what we're looking at here. Okay, a volcano. Great. What is a volcano? What is involved in a volcano? Magma. That's a good word. What else?
A whole like
Ash.
Ash. Good.
Gases.
Gases. I'm liking what I hear. Anything else? Yeah.
Isn't it like a hole into the mantle?
Oh, I was really hoping you'd say a hole to hell, to Hades or hell or something. I was like, okay, Aristotle. A hole to the mantle is an interesting description, an interesting phrase. We'll talk about that. I suppose you could think of it as a tunnel in a way to the mantle, perhaps to the mantle, usually not to the mantle, but we'll talk about that. There's this whole philosophical debate between what makes a hole and what makes a tube. We're not going to get into that right now. All right, let's talk about magma. It's the same sort of question about, is a hot dog a sandwich, right? It's the same sort of philosophical line there. We're not going to become enemies today, so I'm not going to do that. All right, so magma. Let's start off by talking about magma. When super hot rock approaches the surface, okay, usually coming from the mantle, yes, is its source, it is going to enter a melted state for reasons we will discuss here in a little bit. When it reaches the surface, it is called lava. Magma when it is under the surface, lava when it is on the surface. Same substance, just different locations, so to speak. Okay. Why do hot things rise? Do you remember this discussion from the last time we met? Why hot things rise? What do we call the process of hot things rising and cold things falling?
Convection.
Convection. Why does this happen?
Because hotter things are less dense.
Density. By increasing the heat in a substance, you are increasing the energy that substance contains. When you give enough energy to particles, they vibrate faster. All particles are vibrating at a certain speed, right? At a certain rate. They contain enough energy to vibrate. Well, when you put more heat into the equation, aka energy, you cause them to vibrate faster. It is harder for them to maintain those bonds. So bonds break apart. As bonds break apart, you go from a solid to a liquid. As that happens, in most cases, you increase your volume. They are no longer in this tightly bound solid network. They are in a more loosey-goosey liquid sort of framework, okay? And so they take up more space, aka volume, but you have not changed the amount of mass present. Therefore, as mass stays constant, but volume increases, density goes down. Density goes down, that introduces a new thing called buoyancy, okay? That's why boats float. They're more buoyant, aka less dense than the water they rest on. And so as you have new hot melted or melting material, rising up to the surface, that is where our lava, now coming out at the surface, comes from. That's a big part of what we're going to be discussing today, is this process in more detail. Now, someone mentioned earlier that there were gases involved in that volcanic eruption. That's great. That's not usually something that is mentioned, but it is very true. There are 3 phases to the material in magma, okay? Magma in general means a liquid rock, but there are still solid and gassy components to that magma. The gas is actually quite important. That's something that we'll discuss a little bit later today. The solid, though, why would there be solid material in magma? Something that we'll talk about, but I want to pick your brains and see if you can figure it out right now. If I melt something, why would there still be solid chunks in there? Let's hear it here first. Melting points? Not hot enough? Perfect. Those 2 ideas together. If I have a rock like a granite, which I mentioned before and we will learn a lot about today, if I have a rock like a granite, which is clearly made out of a bunch of different minerals, right? You learned last week that there are a whole bunch of different properties that each mineral has. It shouldn't be that wild of a concept to understand that each mineral also has its own unique melting point, right? So if each mineral has its own unique melting point and I start to heat this granite up, I'm going to have some that melt before others. If I have one that melts at 1,000 degrees Celsius, one that melts at 800, and one that melts at 600, and I heat it up to 850 degrees Celsius, 2 of those minerals are going to melt, and the one that melts at 1,000 will not. And therefore, yeah, depending on the temperature of my magma or lava, I will have solid chunks in it. Make sense? No, I'll pass them out in a little bit. Thank you very much. You can go back to your chair. I really appreciate you both. I'll get those M&Ms out of your way here in a minute. So, to understand the concept of convection a little better, here we have a lava lamp. And I used to have a real lava lamp, but the bulb died, and those things are ridiculously hard to replace. But if you know the concept of a lava lamp, you have 2 liquids in this container, one of which is of a different density than the other, okay? Now, as your more dense liquid falls down to the bottom, there is a heat plate here. Think of that as our mantle. It heats up the material, and as that material heats up, its density decreases, its buoyancy increases, and it starts to float up to the top of our lava lamp. This is actually why it's called a lava lamp, by the way, because of this process, if you ever wondered, okay? And then as it gets up there, it cools off, and you can see it's cooling off because its temperature changes. Down here, it's this nice, hot, bright yellow when it's nice and warm, and then comes up here, and it cools off, right? And then it falls back down to be reheated. This is a convection cycle, okay? So when I take a rock like that granite, and I add that heat, and I'm making all of my particles vibrate faster and faster and faster, eventually bonds are going to break, they're going to disassociate from each other, and I end up with a liquid, right? We go from a solid, nice crystalline framework to a more loosey-goosey, hey, I'll bond with you, and then a second later I'll bond with you, and then I'll come over here, or I'll just hang out by myself, either way is cool with me, sort of liquid situation here, okay? Then what happens if we heat it up even more than that? Right, it enters a gaseous state. Think about water, right? What do we call a crystalline framework of water? Ice. And remember, we learned that's a mineral last time, right? So we have ice, you heat it up, you melt that ice, it becomes liquid water. What happens if I heat that water up even more? It turns to steam, and steam is a gas. What's happening here? Our water molecules can't even stand being around each other. They won't bond with each other. They're zinging off in every different direction. That's what happens here, right? They are so energized, they can't bond with anything until they cool off enough to condense on another surface. Okay? So that's what water vapor is. It's the gas phase of this. So I have solids, liquids, and gases in my magma. The same thing, by the way, this process is true of reversing, just like that water condensed to go back to a liquid, so will rock, okay? There's not really at least not very often, will a rock be vaporized. It happens in extremely rare circumstances. When an asteroid impacts, introducing so much energy all at once that it flash vaporizes the rock that it hits. Volcanic eruptions don't generally vaporize rock. A lot of liquid rock, not a whole lot of vaporized rock. Okay? It does happen though. And when it happens, this reverse when you cool things off is true. So whatever our gas is will condense back into a liquid. And then when that loses enough energy, we'll start to reform those bonds to make crystalline solids. However, they may not necessarily form the same thing they were before. If I have the same 3 minerals in my rock and I melt it and it goes through this whole thing and then it recrystallizes, some things may change. I may have new elements introduced. I may have lost certain elements that became a gas and then were lost into the atmosphere and were not reincorporated into the rock. And so I may have different minerals form when I am recrystallizing this process. Also, the speed at which it crystallizes will determine things about it. We're going to learn about all this a little bit more in a little bit. When it comes to classifying igneous rocks, I'm going to teach you 2 words. Now, let me really preface this. I really want people to take note of this, especially my online students who may be washing the dishes or taking care of your kids, or it may just be late at night right now when you're watching this. I want you to listen up to this because someone always gets this wrong. Okay? These 2 words, intrusive and extrusive. Intrusive igneous rocks are the first category. That word means intrusive, they form underground. Intrusive means those rocks form underground. Extrusive, what do you suppose that means? They form above ground, on the surface, or near the surface, okay? The words intrusive and extrusive have absolutely nothing to do with composition. Spoiler alert, on your lab 2, where we learn about igneous rocks, or where you practice what you learn about igneous rocks, I should say, I ask you straight up what compositions of rocks are, of igneous rocks. Do not say intrusive or extrusive. There's always at least a couple of people that do. And that's how I know they weren't paying attention. Because every time I specifically say intrusive and extrusive are not compositions. So if anyone says that on the lab, I'll know you weren't paying attention. Because I have said it enough times at this point. Okay? So what does it mean? Well, what does it matter if a rock is intrusive or extrusive? That tells me a lot about the history of that rock, its origination. How do I know if it is intrusive? Well, let me ask you this. Have you ever put something in your oven, call it cookies? We're talking about cookies way too much in my class, and I apologize for that. You put cookies in the oven, and you cook them, and then you just turn the oven off, but you leave them in there. Versus pulling those cookies out and putting them on top of your oven. And what happens in both circumstances?
The cookies might be burnt in the first circumstance.
Why would they be burnt in the first circumstance? I turned the oven off.
Because it's still hot in there.
It stays hot in there for a while. It is cooling down, but at a different rate than if I took them out, right? My cookies will cool off faster outside of the oven. The same thing is true of rocks. With an intrusive igneous rock, the rocks cooled off underground. With an extrusive igneous rock, they cooled off at or near the surface. Now, what possible physical difference could there be so that I can tell which one happened? Well, if my rock, or if my magma, I should say, has more time to cool down, there's more time for those bonds to form. If I pull that cookie out of the oven right at the time it's supposed to be done, it's going to cool off pretty quick. It's not going to cook anymore. If I cool off magma really fast by introducing it to surface temperatures and pressures, I'm not going to make as many large crystals. They will not have the same amount of time to form that they would have. So how do I tell the difference? Intrusive igneous rocks tend to have large crystal sizes. They had more time for those crystals to form as the magma was cooling off. Extrusive igneous rocks have small, generally microscopic crystal sizes, or near microscopic, very, very small, because it cooled off relatively quickly. That's the best way to tell the difference. So an example of an intrusive igneous rock, this granite. Can you see those crystals? Those mineral crystals? Yeah, intrusive. Cooled off underground, long period of time, lots of time for those crystals to grow and interlock with each other like this. An extrusive igneous rock would be like this one. This is called basalt. I will pass this around here in a little bit, but when I do, you'll notice that you cannot see crystals in it. It's clearly made of them, but you cannot see them, indicating this is what? An extrusive igneous rock. Okay, and just like that, you have learned the first two descriptive words for how we differentiate between igneous rocks, intrusive and extrusive. Now let's talk about compositions. All right, what is composition? Someone tell me what the word composition means. Yeah, what something's made out of, exactly. Perfect. The first composition you need to know is felsic. Felsic igneous rocks are made from mostly light silicate minerals. Remember, rocks are made out of minerals, right? So what minerals our igneous rock are made out of are what determine its composition. Light silicate minerals. Someone remind me what light silicate minerals are. And remember the other term for light silicate minerals? It's non-something. Oh, so close. Your Latin is just a little bit off. That's okay. Non-ferromagnesian. What does that mean?
It doesn't have iron or magnesium.
It doesn't contain iron and magnesium. Okay? Non-ferromagnesian or light silicate minerals. They are going to be light colored as well, right? I'm pulling up this granite again. He's my friend during this class, okay? This granite is a felsic igneous rock. How do I know? I look at the minerals. There are hardly any light or dark silicates, any ferromagnesian minerals in it. It's mostly light silicates. Okay? Now, it may look like there's a lot, but what most of these darker ones you're seeing at a distance, I'm going to hold this up to the camera before I pass this around the room. Most of what those dark-looking minerals are, those are actually clear or gray. That's quartz. Quartz is a light silicate. So you've got whites, you've got pinks, and you've got clear. That's about 90% of this rock, making it a felsic igneous rock, mostly light silicate minerals. Now, there is about 10% or so dark silicate in there. In this case of this granite, it is biotite mica. Okay? That's what those dark black flakes are that you see in there that are kind of shiny when you shine this in the light. Okay? But it's the minority. Therefore, I would call this a felsic igneous rock. I'm going to pass this around going that way. By the way, granite. We like granite. We like using granite. Who has granite countertops or wants granite countertops or has seen granite in the walls of the courthouse or anything? Like we build with granite all the time. Why?
It looks cool.
There are many varieties that look cool. This is very true. It's difficult to break. Why is it difficult to break? Well, look at its nature. It's a whole bunch of interlocking crystals. And most granites are characterized by having high quantities of a mineral called quartz. Do you remember how hard quartz is? On our scale of 1 to 10? It's a 7. Good. It's a 7. It is probably the hardest common silicate mineral. Okay? There are obviously harder ones. Our scale goes to 10, but they are less common by far. And so we like using granite because it has this high quartz content, making it great for things like countertops, where you're using stainless steel. Never, ever, ever build in marble if you can help it. We'll talk more about that when we learn about metamorphic rocks. Marble, not good, not good. Marble's made from calcite. Calcite has a hardness of 3, for those of you that pay attention. Yeah, untreated marble, unless you have an artificial lacquer on top of it, which is harder than the marble itself. Like you drop your butter knife and you'll scratch and chip your marble. Okay, so if there's one thing I want you to take out of this class and walk away with, it's how to not get ripped off by a countertop salesman. Okay, you will know what granite is by the end of today. You'll never get ripped off. I can't tell you, like when I was building my house 5 years ago, they were like, okay, so you can have these counter selections. This is granite from yada yada, this is granite from yada yada. I'm like, you just showed me 10 rocks and only 2 of them are granite. They try. They try. If it looks pretty and they want to sell it as a countertop, they call it granite no matter what it is. Like, if you would like to hire a consulting geologist, I'd be happy to explain all of these to you. And they're like, no, thank you. Just pick one. So I picked granite. Yeah, I picked one of the real granites. Okay. The other, or I should say the next composition is mafic. By the way, if you have a hard time remembering, let's break these words down. Fel and sic. Fel, think feldspar, the most common light silicate, right? Sic is the suffix for silica. Think of that. Silica is the principal thing in light silicates, right? It is a light silicate because it is high in silica content and low in iron and magnesium content, which we will talk about here in a moment, okay? Mafic, dark silicate dominated, okay? Like our basalt friend here. That's basalt, B-A-S-A-L-T, basalt, okay? May, think magnesium, and fic, suffix for iron. Magnesium and iron rich, it is made out of ferromagnesian minerals. There's a lot of olivines, a lot of pyroxenes, a lot of amphiboles in these, okay? This is basalt, and it looks like my camera lost track of me. Hey, buddy, right here. Thank you. Okay, right there, basalt. Now, what's the difference between the granite we discussed that's intrusive, right? Clearly, look at the crystal size. This one, extrusive, microscopic crystal sizes, you can't see any, okay? So if I were to describe that granite right now using the 2 words that we have learned about for it, what would I call that rock? I don't know it's granite yet, by the way. I'm classifying it. What are the 2 descriptive words that I would use to call that rock? Intrusive and felsic. It is an intrusive felsic igneous rock. That's all we know about it so far. That's all we know. We'll learn more about it though. Okay, so here's your basalt, which is an extrusive mafic igneous rock. Okay. Most of the ocean floor, by the way, is made out of basalt. Talk more about that. It is very dense because it is an iron and magnesium rich rock. Okay. Now, the next category, the next type of composition is called intermediate. Anyone want to guess where that one lands? Yeah, right between them. An intermediate igneous rock is one that has approximately equal quantities of felsic and mafic composition, non-ferromagnesian and ferromagnesian minerals, light silicates and dark silicates, okay? About 25 to 50% dark silicates. So it would look something like that. You can tell this is approximately equal proportions of light and dark minerals, right? This one is called diorite. We will talk all about each of these a little bit more here later on today. But this is diorite. Approximately equal proportions of light and dark. And then we have ultramafic. What does ultramafic mean? I knew someone was going to do that. Yeah, it's rare on the surface. Why? Where would this mostly originate then? Yeah, deep underground. In the mantle, actually. The mantle is ultramafic. Why do we call it ultramafic? How does it become mafic? This is something we'll talk about here a little bit later on, called the Bowen's reaction series, about how one goes to another. But ultramafic is where there's absolutely no light silicates whatsoever. All of those are up or near the surface. We're talking about rock deep enough underground that there's none of that. It's all dark silicates. An example of that would be this peridotite that I showed y'all. Did I ever pass this around the other week? No? Oh, I got to pass this around. It's beautiful. Yes. Well, let me show it to the camera again real quick. That green and black mottled rock right there, peridotite, ultramafic. So the mantle's made out of. All right, now, like I mentioned in passing earlier, there is an inverse relationship between the quantity of silica, thank you, the quantity of silica in a rock, and the quantity of iron and magnesium. Now, all of these are obviously silicates. All of them are built around that silicon tetrahedron structure, all these minerals. But when you have more silica and less iron and magnesium in the mixture, you're going to make light silicate minerals out of your magma. When you have more iron and magnesium in your mixture and less free silica, you're going to make iron and magnesium minerals, dark silicates. It's inverse. Think of, the scales of justice. You guys know what I'm talking about when I say that? Where it goes back and forth. When I have high silica content, I will be making very few dark silicate minerals. When I have high iron magnesium content, I'm going to be making very low light silicate minerals, very few. Now, that's not to say that dark silicates don't have a lot of silica in them. When I say high and low, I'm talking about a scale of about 40 to 70% difference there. A high silica content mineral will still have, or rock will still have about 70%. And a low silica content rock will still have about 40% silica in it. Okay? It's just a matter of that scale, high to low. That doesn't mean that there's hardly any. Okay? Which is why when I'm passing around that granite, you see very few dark silicates in there, right? And when I pass around the basalt, there are probably some light silicates in there, mostly plagioclase feldspars, I would imagine. But they're microscopic, just like the dark silicates that make up most of the color. Some of the other behavior of our magma is also related to silica content. For this, let's talk about viscosity. Someone tell me what viscosity is. Like what? Slime is viscous, but so that's an example of something that is viscous, but describe viscosity to me.
Is it the content of water?
Oh, that's cool.
Not content, that's composition, remember? Viscosity is a different characteristic. It is related to composition for reasons that we'll talk about in a minute. All right, fine. Someone can just read it off the slide. It's what? Resistance to flow. Thank you. Okay. Viscosity is resistance to flow. What does that mean? Well, here I have some water. Water is pretty flowy, right? Is that a word? I don't know if it's a word, but it's working right now. It's flowy. It's not a word. Thanks for keeping me straight. Okay. So this is watery. Okay. It flows very easily. As a matter of fact, we tend to use water and the way that it flows, its ease of flow, as kind of our baseline for viscosity. Things are either more or less viscous than water. Okay, there are some oils that flow easier than water does, for example. Okay, but there are plenty of things that flow less easily. Those things are more viscous. For example, wait for it. It's cold enough that it's actually gotten even more viscous than it is usually. This is corn syrup. My classroom is really cold right now. Look at this, though. Can you see it? Can you see it? Look at that. Look at that. It's clearly flowy. It's just not dripping right now. Normally it goes bleh. You can clip that one. I don't care. All right. So significantly more viscous, right? Right?
Yeah.
Work with me. Thank you. Okay, definitely more viscous. It would take me a long time to heat this up with my hands, I think. All right, it's unfortunate. I should have heated it up before. Oh, it's starting to flow. Yeah, it's
Very slow.
right there. You see it going down the side? No? All right, well, I'm going to leave it right here. And in about 5 minutes, you're going to eat your words. Okay. That is corn syrup. Very viscous. Okay. Now, magma becomes more or less viscous based upon its silica content. Why would that make it more viscous? If it has more silica content, why would it be more viscous? Why would it flow less easily? What role does silicon play in the first formation of minerals from a magma? What's the first thing that forms? I'll give you the first part of the word. Silicon. Silicon dioxide is quartz. Huh? No. Tetrahedron. Silicon tetrahedron. Marquez is a geologist. He doesn't know it yet, but he is. He's giving me all these answers. I always have one in my class. He's like giving me all the answers. And they're like, no, I don't want to be a geologist. I'm just like, okay. All right. Silicon tetrahedrons are the first bonds that form in a magma. So if I have more silicons, I'm going to have more bonds right off the bat, right? The more bonds I have right off the bat, the more bonds there are inhibiting the flow of that liquid. So, felsic, mafic. Which composition of magma will flow easier? Mafic, justify that answer. It has less silicates. It has less free silicon. Because remember, it still is making silicate minerals. It has just less free silica to make light silicates. Anyone want to contend for felsic being the easier flow? No? Are we all on board with Team Mafic? You know what would happen to our country if this many people in Congress declined to vote every time? Nothing. Which in some cases might be better. But
exactly what happened.
huh? I'm dropping it down because a few people said mafic and no one said felsic. Do we all agree that mafic flows easier?
Yeah.
Good. Less silica content, easier to flow. Mafic is like water. Felsic flows like corn syrup. Y'all see it flowing now?
Yeah.
All right, good. You understand I'm not crazy. He put glue in there and told us it would flow. Okay. This is a fast-flowing mafic lava flow. Look how fast it's going. These can go pretty fast. Some of them have been clocked at about 35 miles an hour. I hope you've at least got a bike, right? Good luck running from that. Now, this is a felsic flow. This is probably about the same pace most of you get out of bed in the morning.
Molasses.
Right? Why is it flowing so much slower? There are more bonds that are binding up the structure. More bonds have formed earlier, and therefore it is harder for it to flow as a liquid. Okay? It's more bound up. Okay? Yeah?
Would there be any way I could test how much silica is in there before it hardens compared to how after?
Not really before it hardens. But if I were to just instantly cool that, then it would have the exact same content that it did as a liquid. I can't really take liquid lava and put it in one of my instruments. It would melt my instrument, right? These are extremely hot. I'm talking like even the coldest lava flows are still about 400 degrees Celsius. Yeah, that'll melt anything I put it into, right? But if I flash cool it, like if I just, and people do this, they go up to these lava flows, you have to be in heat suits. You just take like a hammer or a collection tool, you just like stab it in there and yank a bunch of lava out and then back off real quick, because even in a heat suit, it'll kill you, okay? You just basically go and pull it back with you. So you got basically this long string of lava that almost instantly cools into rock after you remove it from the rest of the lava. That I would test to figure out silica content and every other attribute that I want to know about it. Speaking of lava flows, I'm going to play this for you. And I hope my volume is on. Okay, should work. I want you to listen. You're going to hear some wind. I want you to listen past the sound of the wind towards the sound that this lava flow is making. Hold, please. Apparently the wrong speaker is connected. Again? Yes. Okay, but now it's saying the right one. Oh, it's muted. Okay, let's try this again. Lava flow sound, take 2. What does it sound like?
Like rocks.
Like glass.
Like glass? Oh. That sounds more like glass.
My projector doing its thing, cutting in and out. All right, it sounded like what? Did you say it sounded like rocks? Like just pointing at each other. Who said glass? Good. It sounds like shattering glass. It's way louder in person, by the way. This camera couldn't pick up a whole lot of it, and the wind counts some of that. It sounds like 1,000 dinner plates all shattering at the same time, constantly. Just it keeps going.
It's like a bunch of glassware in a dryer.
Yeah. Oh. You said that far too confidently to know what that's like. Your poor mother. All right. Now, glassware in a dryer. I would never use that dryer again. Like all of my clothes would be. Oh yeah. I lived in Hawaii for 3 years. I've been near a number of lava flows. I did not take this video personally, but I have been about this close to a flow before. A little bit further, maybe 10 feet further back than that, but it was still deafening. The sound of shattering glass. Why does it sound like shattering glass? Huh?
Hardening and then melting it all over again.
Oh, that's great. It's hardening and then melting and moving and breaking. But why the sound of shattering glass?
Because
It's like a glass.
How do you make glass?
We melt it. Heat it up to where it's almost like that, so you can like hold it the way you want it.
I love all of that except the word it. Heat what up?
silica.
Sand to make glass, right? But sand is
Silica.
silica. It's quartz. Sand is quartz. So if I have a flow that is rich in silica, which will later go on to form quartz later on, right? But it's cooling off really quick, it's going to make volcanic glass. Where is it going to cool off the fastest? Where's my flow going to cool off the fastest?
Surface.
The outside. Look at the outer surface of this. It is cooling off very quick in these conditions. It's very windy, right? It's probably cooling off the outer surface of this flow very quickly. And so it is making volcanic glass on the outer surface. But as the flow keeps moving, it keeps shattering and pushing that glass. So you're forming and then shattering and then reforming and reshattering glass all across the entire surface of this flow. That's why it's making that sound. What's another word we have for volcanic glass? Obsidian. Thank you. Obsidian. Literally glass. This is how we make glass. Every piece of glass that you see in this room was made through the rapid cooling of melted minerals. Probably a quartz or some other substitute, depending on the glass and what it's going to be used for. Okay? But you make glass when you cool off lava really quick. Now, the composition of your lava flow will determine the color of the glass that you make. for example, a very silica-rich, very non-ferromagnesian rich, right? So very little iron magnesium will make a more clear sort of glass. Like this. Daisy, look at that and tell me what you see inside of it.
Bubbles?
Bubbles! Why would there be bubbles in this glass? Yeah, sure, it's air, but why?
It couldn't escape.
Ooh, it cooled so quickly that the air bubbles couldn't escape. Good. It cooled that fast on the outer surface of the flow, right? I'm going to pass this one around now. Now, most obsidian that you see, that's the word we have for it is obsidian, right? Most obsidian that you see is going to be very dark in color, but there are a few other varieties. Here's a pretty cool one. This is called mahogany obsidian. It's mostly black, like most generic obsidian that you would ever find, right? By the way, what do you suppose the black color indicates? Iron and magnesium. What about the red?
Iron?
Yes, this is partially oxidized iron. Yeah, wow. You can have all sorts of varieties of obsidian. I'll show you a picture that shows you more here in a little bit. Here you go. Okay. Now let's start learning a little bit more about classification. So we've learned about intrusive and extrusive igneous rocks. We've learned about compositions. Now we're going to learn about igneous textures. Textures is another characteristic that we use to describe igneous rocks so that we can tell them apart from each other. They are determined by the rate of cooling, predominantly. Things like the amount of silica and what sort of volatiles, like dissolved gases, were in there can also affect your texture. It mostly has to do with the rate of cooling, though. The first one I'm going to show you is volcanic glass. I actually showed you a few. Are you looking through it like binoculars? Can you actually see him better through that? Take off your glasses. It might help. It's not going to help. Okay. This is prescription obsidian. Hey, look. Look at that. It's doing its thing now. Yeah. How viscous that is. When you take a lava and you cool it really quick, that's when you get obsidian. It's called quenching. I've done this before. I wish that I could find this. It's in my personal collection in my spare office somewhere in there. But I have a bottle with 2 tiny little pieces of green volcanic glass in it. From when I was doing my undergrad, I was getting my bachelor's degree in Idaho. I took a small piece of basalt, I crushed it to a fine powder, and then I used a welding torch to heat it until it reached its melting point, and I had lava in a tiny little crucible. And then I dumped water on it, and it instantly quenched. And I took it from this black chunk of rock about this big, and I made 2 little green glass beads out of it. When you quench a lava, even though it may have come from like a basalt, you still got glass. Yeah.
Did you make a nether portal?
Did I make a what?
A nether portal?
A nether portal?
Yes, out of the obsidian.
It's a Minecraft question, isn't it?
Yes,
Yes, it is.
Of course
There's
it
a lot
is.
of similarities, I've noticed.
Oh, are there?
Yes.
I'm glad you see a lot of
Geology just
similarities.
Minecraft?
No.
I like that question.
Is geology just Minecraft? No, but Minecraft has a little bit of geology in it, and some of it's even right. Not much, but some of it. No, I've never made a portal by crushing obsidian and doing anything with it. Good question, though. Thank you. And so you'll end up with something that looks like that if you do that. That's quenching it, okay? So that gives you a sort of glassy texture, we would call that. There aren't any grains. There's no crystals in there to classify it with. So we just call it a glassy texture. Now, the first real texture that you get is aphanitic. Aphanitic igneous textures are those with microscopic crystal sizes. Now you're thinking to yourself, wait a second, didn't we already learn about that? That's extrusive. You are correct, but extrusive is a description of cooling environment, not a texture. the texture for a microscopic sized or crystal sized igneous rock is aphanitic. That's me officially saying it has microscopic crystal sizes. Classic example is that basalt I just handed around, right? You couldn't see any crystals in it, therefore aphanitic crystal sized. Now, an additional textural observation here has to do with these bubbles. You see these bubbles in this rock? If any of you passing around that basalto, you may have noticed that there were a few bubbles in it. But like this one, for example, is full of bubbles. I'll pass this one around here later, okay? But in these examples, you see full of bubbles. Up here, tons of bubbles. To figure out what those are, let's look at this picture. This is a solidified lava flow. Tell me what you observe about the difference between the bubbles here and up there. There's bigger and there's more of them the higher up you go. This is the inside of the flow, and this is the outer edge of the flow. Why would the bubbles have more to do up here? Why would there be more bubbles up here than there were down here? Not density. Not convection. The gases are trying to escape from this flow. As my flow is cooling off, it is making gases. Solids are forming out of liquids. That means there's some extra stuff left over. There's some extra carbon dioxide. There's some extra sulfur dioxide. There's extra water vapor as a result of going from a liquid to a solid. Now, as these gases are forming, they're making little bubbles. They're making little pockets. And they're going to try and go where? Up to the atmosphere, outside of the flow. But the closer they get to the outside of the flow, what's happening? Huh? It's getting cooler, which means the outside of my flow is hardening, getting cooler, hardening, which means that before the bubbles can escape, they get stuck there, and there they remain in the rock. Yeah. As a matter of fact, the bubbles in that chunk of glass that's getting passed around right now, it is quite common. There are scientists that devote their entire careers to this, to harvesting the volcanic glass from these ancient flows, going and then micro drilling down into those gas bubbles to extract the gases that have been trapped in that glass for millions of years, and analyzing it to figure out more of the chemistry of that rock when it was a lava. It's pretty cool. You can learn a lot by doing that. But these gases were trapped in this rock for that reason. We call these holes vesicles. That's this word right here, V-E-S-I-C. And then in this case, the texture would be vesicular. The holes are vesicles, C-L-E-S, right, on the end of that. But vesicular is how you would describe this texture. So if I were to hand you a chunk of basalt with holes in it, what are some words we would use to describe that? It is an extrusive, mafic, aphanitic, vesicular igneous rock. These descriptive words are what we use and what you all will use in the lab to identify what you're looking at for lab 2. Okay? Are you following me? Yeah? Have I started to lose any of you yet? No? I'm seeing a few yawns. Okay. I went to a wedding the other day between 2 satellites. The wedding wasn't much to talk about, but the reception was incredible. Good. Yeah, you got there. You got there. Yes. Okay. The next texture is phaneritic. Phaneritic is the texture for when you have easy to see crystals. Okay. Up to, we'll call it 2 centimeters. Anything larger than that goes into another category we'll talk about in a minute. But from just barely visible up to about 2 centimeters, we will call that phaneritic texture. An example would be that granite that I just passed around. Okay. Now, what does this mean? This means that it cooled underground, it cooled slowly, lots of large crystal sizes, all of that easy to see, perfect. Now, this is true regardless, but these textures are possible regardless of composition, by the way. This is a phaneritic felsic igneous rock. This is a phaneritic mafic igneous rock. This is a phaneritic, intermediate igneous rock. Okay? Compositions and textures are totally different, and we can mix and match. I'll actually show you a little grid here in a minute that shows you that. Porphyritic. Now, this one's new. This is a combination of phaneritic and aphanitic, where you have a lot of microscopic sized crystals, but also you can totally tell that there are large crystal sizes in there as well. Under what circumstances, do you suppose, would we have both microscopic and large crystal sizes in the same rock? We talked about this earlier, actually.
Or it goes right in the middle. And instead of exclusive and inclusive effect.
I think you're getting there, but you're not using the right words.
The big crystals had a higher melting point.
Ah, there it is. There are two ways you can get this. I think that's where you were going. You just couldn't find the right words, right? Yeah, I acknowledge that. Okay, so there are two ways you can get to this. You can either have a rock that partially melts, say melting 2 or 3 of the minerals in it, but not all of them. There's maybe 1 or 2 that don't melt. And so you get magma with the rest of this solid stuff floating around in it, and then it cools off quickly, meaning that the magma cools into tiny crystals surrounding the original larger crystals that were left behind, right? Or there's the other option, that the larger ones are there from a different rock, or it started to cool slowly. This is a completely melted magma at one point, and it starts to cool underground slowly. And as it does so slowly, you start to make larger crystals. And then after you have a few larger crystals, all of a sudden, the entire mass of magma gets shoved to the surface and the rest cools quickly. So these large crystals are either relics from a previously existing rock, or were the result of slow cooling and then rapid cooling at the end of the cycle of the magma. Those are the two ways that you can make this porphyritic igneous texture, a combination of both aphanitic and phaneritic, microscopic and easily seen crystals. Yeah, of course. And then there's glassy, right? I promised you I'd show you this picture, the different varieties of obsidian we have. I showed you mahogany. I passed around the mahogany obsidian, right? Somewhere, I think. Oh, you've got it. Okay, perfect. Okay, mahogany obsidian. Rainbow obsidian has a whole bunch of colors in it, as the name implies. Golden sheen, it looks like gold. Fire obsidian it's beautiful, got that green and red. Blue sheen, obvious why we call it that. Snowflake obsidian, I have a bunch of this. I don't have any out here, but snowflake obsidian is actually really old obsidian. It's what happens when obsidian starts to break down. Okay, what we're calling these snowflakes in here is actually where the glass has started to deteriorate into a chalky sort of dust. Okay, but you can get lots of different varieties based upon what the rock or what the composition of the lava that it formed from was. There's a really fun variety in places like Hawaii, where you have very non-viscous, so remember, easily to flow. Places like Hawaii have a lot of mafic lava. And so the lava gets spat out, and as it flies through the air, it kind of makes these thin stringlets, and they fall into the ocean. This lava gets spat out, and these thin little stringlets, and if they fall into the ocean, get instantly crystallized into thin strands of obsidian. And then they wash up on the beaches in these bunches of long strands of glass. They call this Pele's hair. If you're familiar at all with Hawaiian culture, Pele is the Hawaiian goddess of fire and creation, okay? Because that's where the new lands, that's where the new islands come from the volcanoes. They call that Pele's hair. That is a pretty cool variety of obsidian that you can find. So that's glassy texture. Then there's pyroclastic texture. Pyroclastic textures, this is an interesting exception to our rule of igneous rocks, I suppose you could say. I told you earlier that igneous rocks can only be formed from the cooling of magma, right? This is the one exception. Pyroclastic rocks are made through volcanic eruptions. For example, a volcano erupts and jettisons millions of tons of ash into the atmosphere. Where does that ash go? It doesn't just drift off into the sunset, never to touch the ground, right? It falls to the ground. I have a vial of Mount St. Helens ash here from 1980, right? We'll talk more about that, believe me, on in our next lecture. We'll talk about volcanoes in general, specifically. But when you have a whole bunch of ash and debris that gets blasted out from a volcano and then it falls to the ground, it's often so hot that it fuses together and makes a new type of rock. That is a pyroclastic rock. So even though it's not directly the result of magma, it is still from a volcanic process, and therefore it is called an igneous rock. So here is an example. This is called a volcanic breccia. This is a whole bunch of ash and just absolutely shattered, pulverized rock from a volcano that all got fused together in the wake of that eruption. Okay? That is a pyroclastic texture. Sometimes this can be confused with sedimentary rocks. How do you know if it's a pyroclastic rock or the result of a whole bunch of sediment that got compressed together? There are ways we can tell. For example, a pyroclastic rock will not be made out of crystals, weathered pieces. It won't be made out of, sedimentary rocks will be more weathered. They'll look like actual crystals. Also, you can confuse this with something like other igneous rocks that have well-formed crystals. These pyroclastic rocks will always be made out of fragments. Okay, blasted debris is what it looks like. Not well-formed crystals, not sediments that got compressed. Okay. And then finally, pegmatitic textures. Pegmatites are really cool. Pegmatites are what you get at the very end of the life cycle of a magma chamber. So my magma chamber has slowly been cooling down over time, and we'll talk more about this process here in the next few slides, but it's slowly cooling down over time. And as it does so, all of the elements that were in that magma that do not easily bond with anything else, like our rare earth elements, for example, they are forced to now enter a solid state, which means that as these pegmatites start to form at the end of the magma chamber's life, they make very large crystals, which are often rich in rare elements. This is a picture from the Nica mine in Mexico. That is a person right there, by the way. My great uncle is a geologist, worked out here in Texas as a petroleum geologist for about 30 years. He had the opportunity to go to this mine at one point back in the 80s, I believe it was. I have a picture of him somewhere standing, like leaning up against that crystal. It's been illegal for a few decades for people to go in there now because it's a protected heritage site, so they don't let anyone go in anymore. I wish I could. I would already have gone if it was available, if it was an option. But that is a pegmatite. Massive crystals, very rich in rare elements. We get all sorts of rare stuff out of these. If you ever go to South Dakota to see Mount Rushmore, and if you ever seen Mount Rushmore, yeah, that entire area, by the way, Mount Rushmore is carved out of granite. That granite goes up, it's right up against a pegmatite. There's a lot of mining that happens out there in the Black Hills because of the presence of that pegmatite. And this is the texture that we use to describe any rock, any igneous rock that has larger than 2 centimeter sizes. Okay, so I told you phaneritic ends at 2 centimeters. Pegmatitic picks up at 2 centimeters and on. The largest crystals that have come out of pegmatites, they're actually pretty big. There are 30-foot crystals that have come out. The largest feldspar crystal ever found in the world, which, by the way, this is a feldspar crystal right here from a pegmatite. The largest one was the size of a 2-story house. Yeah, they get big in pegmatites. Okay. Any questions about textures? We've learned about compositions. We've learned about textures. Let's talk about how we use all this information to classify them now. So things like the cooling history and the, thank you, and the composition, its situation on underground or above ground, all of that are factors into what make an igneous rock the igneous rock that it looks like, that it is. So we can classify them based on texture, their composition, all of these things. This is kind of a general use. This will not be perfect for your lab. I give you more samples than are present on this, but this gives you an idea, right? If it has phaneritic texture and is felsic, boom, granite in this particular circumstance. Phaneritic texture and intermediate, boom, diorite, okay? This is how we use all of these properties to identify what we're looking at. Here's a simpler example of that. A mafic porphyritic rock would be called a basalt porphyry. Super original, right? A mafic aphanitic rock would be a basalt. We saw that. A mafic phaneritic rock would be a gabbro. I'll show you some of that in a minute. So using this sort of framework is how you will use those properties to identify what you're looking at on your lab. Lab 2 will be assigned after our next lecture, by the way. You won't get it today because you need the next lecture in addition to this one to understand all the material. Gives you a little more time with lab 1 as well. Okay. So let's talk about some of the more common rocks that we're looking at. The most common igneous rocks that you'll see. So granite, and I will pass this around again because now you understand a little bit more about it. Granite is an intrusive, felsic, igneous rock with a phaneritic texture. Right? You understand all those terms now. We use it a lot for building materials. Why? Because it has a lot of quartz in it, and quartz is hard. The other minerals in there are pretty hard as well, but quartz is definitely the main reason. Okay? Granite. There are lots of varieties. They won't all look like that, right? There are brown granites, and there are some granites that are almost verging on black. There are granites that have so much quartz that they're almost clear all the way through. There are granites that are blue. There are granites that are yellow and pink. It just really depends. The color of the feldspar variety in there is a big factor. Now, if I were to take the same felsic composition magma that made that granite, and instead of allowing it to cool slowly, I made it cool quickly, I would have the exact same composition, but my texture would now be aphanitic, right? And if that happens, I end up with a rhyolite. Rhyolite. There are a few crystals in there large enough to see with the naked eye. Sure, great, awesome. But most of them are microscopic. Okay? The exact same thing as the granite. If I knew that these came from the same flow, but one of them cooled underground in the magma chamber and one of them cooled in a lava flow on the surface, I could measure them chemically and find them almost exactly the same. The difference is how quickly they cooled. This is the aphanitic version. Okay? If I were to take my magma and quench it immediately, you would get that glass, okay? That glassy, textured obsidian. How many of you like soda? I'm not a huge soda guy myself, but I do know some things about it. If I were to take a root beer and shake it up real good, and then pop the cap off of that, what would happen? Huh? It would fizz up. Yeah. That's going to be very relevant to our conversation later on. But the first thing that comes out of your bottle is going to be foam. That fizzy stuff, right? It is filled with so much gas that the substance that is my soda is filled with all the gas, and this gas is forcing some of the soda out, but it's mostly gas. The same thing happens with lava. When I have so much gas in my lava that it fills that liquid up and causes it to come out of my volcano, It almost instantly cools like that. There's very little actual lava in there. There's so much gas that it fills that lava with all of these holes. It's so filled with vesicles. And between all these vesicles are thin little walls of glass. We call this pumice. Let me go to the next slide. Pumice. How many of you have ever used pumice stone on your skin or at a spa? Yeah. This is where pumice stone comes from. It is a volcanic rock. When the volcanic material, aka your lava, is filled with so much gases and cools so quickly that you get an extremely air-filled version. Okay? Now, this is so filled with holes. So much of the volume of this is air, because it's all holes, that it will actually float on water. Yeah, pumice floats on water. All right, that's the felsic rocks. Let's move on to intermediate. The intermediate aphanitic igneous rock is called andesite. Remember, intermediate being somewhere between felsic and mafic. Okay, so you can tell it's got a generally darker color than that rhyolite did. You can actually see some of the larger crystals in there are dark colored. Okay, clearly intermediate, mostly aphanitic. There are a few larger crystals, but it's mostly aphanitic. This is called andesite because most of the Andes mountain range in South America is made of this. This is where it was characterized. Okay, this is where it was really studied for the first time by someone. Okay, andesite, Andes, you get the idea. The intrusive phaneritic version of andesite is diorite, which you all already saw, but I'll pass around again. Same composition as andesite, just different cooling history. Some people call it salt and pepper rock. Please call it diorite. By the way, that is another one of the rocks that people try to market as granite all the time. Is Abby asleep? Okay. Someone poke her. I didn't mean to do it on her forehead. You okay? Yeah, I know. Early morning classes are the worst. All right. Should I tell you another dad joke to wake you up?
I need a guy.
What? You have so many notes already? Good. I'm glad you have so many notes.
Anthony, we would like to hear that.
You would like to hear a dad joke? All right. So we had an event to go to on Saturday night. We were getting ready. My wife asked me to pass her lipstick. I accidentally passed her a glue stick. She still isn't talking to me. Okay. All right. So basalt. Basalt is our aphanitic, mafic, extrusive igneous rock, right? Very, very common. Actually, the most common extrusive igneous rock on the surface of our planet. Why? Oh, at least you're honest.
It's in the ocean.
Ah, and what does the ocean cover? 70+% of a planet's surface. Basalt being what is under the ocean. Okay? Boom, bada boom. Logicked. The most common extrusive igneous rock on the planet.
If I believe hard
Okay?
enough,
Now, the phaneritic, intrusive version of that is gabbro. You will notice some larger light-colored minerals in here. There are going to be a few in mafic rocks. Ultramafic are the ones that have none. Mafic will have a few, but it's a little bit deceiving in this particular sample because of a lot of what looks like a light-colored mineral is actually where some student has dropped it or hit it with another rock. And so it's kind of chipped a little bit. So there's a fractured surface that looks light, but most of this is dark, just like that basalt. It's just that you can clearly see cleavage planes and crystal surfaces of all these minerals, right? Indicating that they're large enough to see with the naked eye, and therefore it's phaneritic. This is gabbro. Another common building material. Our pyroclastic rocks. I already passed around the volcanic breccia, right? Like this. Another one is welded tuff. Tuff, so that volcanic breccia is when you got the ash and the fragments from your volcanic eruption that got welded together. A tuff, T-U-F-F, by the way, volcanic tuff, is what you call it when you just have a whole bunch of ash that made layer upon layer upon layer and got fused together because it's still really, really hot when it goes from the atmosphere to the ground, okay? So this is a tuff as opposed to your volcanic breccia. All right. Any questions about these common igneous rocks that we just passed around? Are you lifting my rock to work out?
Something like that.
All right. I mean, I know it's dense. I didn't think it was that dense.
It's not.
All right. Where does magma come from?
Underground.
Underground. Solid answer. The mantle. All right. Is the mantle liquid, though?
No.
No. So where does magma come from the mantle? A lot of people learn this in school still, which is disgraceful in my opinion, but I'm going to teach you why it's wrong so you know better, okay? Magma, we are not just floating on an ocean of magma, okay? We've known better than that since the 60s, okay? Our continents aren't just playing bumper cars on an ocean of magma. We are on top of a solid surface of mantle, which is hot enough to be melted, but under enough pressure that it cannot be. So it is, in fact, the process of convection that moves our tectonic plates around and all of that. So if that is true, if we are a solid on top of a solid layer, then where does melted rock come from at all? Huh? That's a possibility we'll talk about. At some point, something has to change. A condition somewhere has to change, be that temperature or pressure, to allow some of that solid to enter a melted state. This is where the geothermal gradient comes in. Now, the geothermal gradient is the rate at which temperature changes the deeper you go underground. Okay? It's not, I mean, you all should know the deeper you go, the hotter it gets, right? I go caving all the time. Okay? If you're interested in seeing, I have on my YouTube channel, the same one that I give you those lab videos on, I actually have caving videos on there as well. Okay? The deeper I go underground, the hotter it gets. It's actually usually high 70s, early or like low 80s, and very humid when you get down into the depths of these caves. You're sweating, not only from the exertion, because of how hot it is. Okay? Why does it get deeper the deeper you go underground? The geothermal gradient. To understand this, this is the Tautona mine in South Africa. This is the deepest mine in the world. When this graphic was made back in, I want to say 2015, it was 3.6 kilometers deep. It is so hot down there, it's one of the places in the world that they are exploring robotics the most. Because if you can have robot workers at the bottom of your almost 4-kilometer deep mine, then you don't have to put your employees in a refrigerator once every hour. They have to do that. Their employees can work for an hour, but then it gets so hot to keep them from dying of heat stroke, they have to go stay in a refrigerator for a little bit. Yeah. So it is so extreme that this is where they're exploring robotic mining. One of the places where they're getting the furthest with that, because they're experimenting a lot with it. So it gets hotter the deeper you go underground because you're getting closer to the center of our planet. The center of our planet is still really hot because of all the radioactive stuff still going on and cooling from all the heat that it had when it was made, right? So this is our geothermal gradient. On this axis, we have depth. This axis is temperature. This axis is pressure. Why do we have pressure and depth on the same axis? Because they are consistent with each other, okay? Pressure increases at the same rate that depth does. So temperature up here on the opposite axis. Now this hockey stick shape is our geothermal gradient. Notice, if you will, that here we have the melting point of peridotite. Peridotite being the rock that makes up our mantle. Does our geothermal gradient and the melting point of our peridotite ever touch? No. Therefore, the mantle is solid. Somehow, these two things have to touch for melting to happen. There are three ways this happens. The first one, tectonic activity. Oh, I already have it out. Let's grab it a different, let's see, maybe dark green, maybe red. I'm hoping red will show up well on the camera. Okay, so tectonic activity. If I have a continental plate and an oceanic plate is subducting underneath of it. You said a word earlier, friction. These two plates grinding past each other. Do you think that's going to make some friction? Friction makes what? Heat. What happens if I increase the heat? My geothermal gradient, which is the temperature at that depth, right? If I increase the temperature at that depth beyond what its default would be, all of a sudden, my geothermal gradient overlaps the melting point, does it not? There you go. We have magma, the potential for magma right there. Okay, so we can increase temperature in some way, this being one example. What's another way? Decrease the pressure. Where would this be possible? Well, let's say that we have two oceanic plates that are diverging away from each other, a divergent plate boundary. Because they are pushing away from each other, there is a zone right here between them. Oh, that was a painful noise. Right there, where the two plates are the thinnest, because that's where they're being made, where the mantle can push up between them and approach the surface. And therefore, as it gets closer to the surface, what drops? Pressure. So if I am at, let's say, 50 kilometers of depth right here, or 100 kilometers of depth, let's call it, okay? And I drop the pressure, so the pressure goes up, I shift this hockey stick up like this, all of a sudden, right there, I am now past that geothermal gradient, or past that melting point. So by decreasing the pressure, I can also make melted magma, melted rock, magma, okay? So I get a pocket of magma right there because of the lower pressure. And the third way, this is the fun way. This is my favorite way. Can I have a favorite way to make magma? I guess I can. You change something about the chemistry. This is all consistent based upon consistent chemistry. Things that have been proven in a lab setting. But what if I can change the chemistry? What if I can change the melting point itself? Now I'm going to say this here, and y'all are going to think I'm nuts. And I'm sorry, I'm not going to justify it chemically. We don't have that kind of time. And I doubt y'all have the same chemical background. Okay? So you're going to have to take my word for this and investigate it on your own later on if you'd like. Water lowers the melting point of rock. What? How is that possible? Water is like the opposite of heat. If my computer lit on fire right now, I'd look for something to put it out. I might go put it out before it burns the building down, right? I use water to cancel out heat. We use water to put out fires. We use water to cool things down. How can water lower melting points? Using water to absorb heat is one of its physical characteristics. However, one of its chemical characteristics is that when you introduce the chemical water, H2O, to a crystalline matrix of a mineral, or in this case, our really hot rock, it lowers the melting point of that substance. So if I were to lower my melting point, so here I am at 100 degrees, or excuse me, at 100 kilometers. Normally, my melting point is right here at that depth. What happens if I then take this melting point and move it that way down my temperature scale? All of a sudden, they overlap. And I have magma. Where would this happen? Let's go back to our example here. Let me lengthen out this oceanic plate. This has been happening for a while. It's been subducting there for a good long time. This oceanic plate has what on top of it when it's out in the ocean? Water. I don't have a blue pen, apparently. It's got water on top of it. It is saturated with water in the top layers of this rock. That water is getting carried down into the mantle with it under that continental plate. As that water heats up, what's it going to do? It's going to make a gas. And where's that gas going to try and go? Up. So I have water leaving this oceanic plate and making its way through the mantle to try and get back up to the surface. And what is that water going to do to the mantle right there? It's going to lower the melting point. And because it's already hot enough that it would melt if it could, it does. And you get pockets of magma down there. And it is these pockets of magma that rise up to the surface and make our coastal mountain ranges. That's where you get your Andes. That's where you get your Cascades. That's the word I was looking for. The Cascade Mountain Range, like out in Washington and Oregon and all those places. Okay, that's where these coastal mountain ranges come from, is because of this process. These are the three ways that you can make magma out of the mantle: increase temperature, decrease pressure, add a volatile that lowers melting point. Does that make sense? Yeah. Yeah. We good with this? Great. All right. Now, in our magma chamber, things are happening. It was believed for a long time that a mafic magma chamber was just a mafic magma chamber, and a felsic magma chamber was just a felsic magma chamber, and they spat out whatever magma was there in that chamber. However, it didn't really make a whole lot of sense when you think about it over time. So this gentleman named Bowen, okay, N.L. Bowen, performed a series of experiments to determine whether or not the nature of magma chambers will change over time. And what he found was that, yes, as a matter of fact, as the temperature, the overall temperature in your magma chamber decreases over time, the type of minerals formed will change, and that will in turn affect the composition of the magma present. So if I have a magma chamber, a fresh, brand new magma chamber, just arrived from the mantle, it's just at the bottom of our crust, it's making its way up to the surface. What's the composition of the mantle? Do you remember? Where'd my peridotite go? Oh, it's right there. What's the composition of my peridotite? It's not just mafic, it's ultra-mafic, right? Every time I say that, I think I'm introducing like a superhero or something. I'm ultra-mafic man, right? No, it's ultra-mafic, okay? That's what our first magma chamber out of the mantle is going to be. That's going to be its composition. So here I have an ultramafic composition magma chamber at about 1200 degrees Celsius, by the way. Whew, that's hot. Okay? As it starts to cool, the first minerals start to form. The minerals that crystallize at 1200 degrees Celsius start to form. That's olivine. Olivine is a dark silicate rich in iron and magnesium elements. The more olivines that I form over time that require iron and magnesium, the less iron and magnesium is left in the magma. You following me on this? I'm pulling iron and magnesiums out of the magma to make my olivine crystals. That means that as time goes on and I make more olivines, and then eventually I start making other things, I'm going to be depleting my magma out of whatever was required for those minerals. So eventually I'm going to go from an ultramafic magma composition to a mafic magma composition because I have pulled so many irons and magnesiums out to make those olivines. And then I'm going to start making pyroxenes and amphiboles and plagioclase feldspars. And eventually I'm going to have pulled so much stuff to make out all of those minerals that my remaining magma is now intermediate. And then I'm going to start making other things, my biotite micas, my sodium-rich feldspars, until eventually I have pulled so many things out that I am left with a felsic composition chamber. All of this happening as temperature decreases, which therefore new crystals form, which therefore pull things out of the magma, changing the overall remaining chemistry of my magma chamber. Meaning that all magma chambers start ultramafic and die felsic. This is Bowen's reaction series. And we're going to experiment with this concept right now. Everyone's going to get a bowl of M&Ms. I'm sorry for my online students, you don't get M&Ms unless you really want to buy some for yourself. But luckily, I have a graphic that will go on the screen to demonstrate. I'm just going to stack these up and carry them around. Please refrain from eating your M&Ms until after we are done with the demonstration. And then they are all yours. If you don't want them, feel free to leave them on the table. Yep. Or throw them away. It's up to you. You got one, right? Okay, good. There you go, bud. Cool mouse. Okay. Ruh-roh, am I short? Did we make 22 of these? I'm too short. 2, 4, 6, 8, 9, 10, 12, 14, 15, 17, 19, 20, 22, 24. Yeah, some people walked in, huh? Oh, 25. Okay, yes, we are 3 short. Yeah, we're gonna have to make 3 more real fast. When we started, there were 20 people in here, and I thought 22 would be safe. Let's see. Three, 4, 5. 3, 4, 5. 4, 5. Sorry, I'll sweep up later. Oh no! Would you mind putting 2 of those browns in each one? I think I put 6 in there on accident. All right, while y'all finish that up, I'm going to grab these papers and hand them out. All right, now in addition to your bowls of M&Ms, I have a paper for each of you. Meet your magma chamber. I'm going to have another one just like it up on the screen, and I will digitally show my online students up there what my in-person students are going to be doing on these papers.
There's too many.
There you go. I think I gave you 2. Would you get one to her?
Wait,
You need one
is
as well.
there even white in there? If there's They're not.
Here. There.
Yeah. Because I remember some like white chocolate that were really good.
There you go.
They got stuff.
Extra.
Extra chance.
We only get a few holidays.
There you go.
And then they go back to being.
Okay. Okay, this is 2. Would you hand one to him as well? There you go. There you go. Yeah. And there we go. Okay. Okay. Ooh, awesome. These bowls are ready to go. Thank you so much to my assistants today. Greatly appreciate you. One here, there, and then one over here for our missing friend. All right. Now, notice on your sheets of paper that you have the chemical equations for a variety of minerals, all of which we have discussed in our class. You see they're there in the bottom picture, in the bottom part of the picture, in the bottom part of your paper, I should say. I have the chemical equations as well as what the colors of each M&M represent. For example, yellow is, Jose, what is yellow?
Calcium.
Not Jose, thank you.
Oh, my bad.
It's okay. Blue, what's blue? Aluminum. Good. Okay, so you're following the concept. Now, I have not given you a color for oxygen because there are oxygens bonded to all of these. Notice you have 30 silicons. If I gave you oxygens, whatever color oxygen represented would fill up your bowl. Okay, so oxygens are implied for this experiment. Okay, we're just doing the non-oxygens for this. So we're going to start off with a brand new, fresh, out of the mantle magma chamber. What's the first mineral that's going to form that we just learned about? It's going to be olivines. What's the chemical equation for olivine?
I'm not reading all that.
You're what?
I'm not reading all that.
You're not reading all that? Huh? Iron, magnesium, and silicon. Okay, good. So you'll take, and this is interchangeable. Irons and magnesiums are interchangeable for this one. But to go ahead, 2 purples, for, let's say, and your silicon, your orange. Okay? We're going to make it, and it's going to go down here at the bottom of our magma chamber. Why? Because it's the first one that forms. If I were to take a bottle of water like this, and then dump sand in it, where would the sand ultimately go? The bottom. Our first minerals tend to filter down to the bottom of our magma chamber. So they go down to the bottom of our magma chamber, where, by the way, I also have a scale that shows you what temperature these things all form in the order. So at about 1200 degrees, our olivines form. That's where they end up. Okay? Next up, we make our pyroxenes. What's the equation for pyroxene?
Magnesium, iron, silicon.
Good. Make it, and it goes down here just above our olivines. What has happened to our chamber thus far? We have less what? Irons and magnesiums. We have now left the realm of it's so rich in iron and magnesium that we call it ultramafic. And we have now entered the domain of just mafic because the ratio of irons and magnesiums to the remaining elements is off. It's off because of the quantity of olivines and pyroxenes that we've made. Now let's make some amphibols. And whoo, that one's a doozy. Someone tell me what's in our amphibole. A little louder.
Calcium, magnesium, iron, silicon.
Calcium, magnesium, iron, and silicon. Go ahead and make those. And those are going to go down here. You don't have to have them all in a nice, neat line. You can have a pile of them to represent each one, right? Do it how you're going to do it. But the point is that you get what I'm saying here. We have made amphiboles now, which has even more reduced the quantity of remaining irons and magnesiums in our magma. Oh my goodness, my camera's not even looking at me. My online students are going to have been yelling at me in the chat for like 5 minutes. Hello, hi, right here, yes. All right, chat. Well, we've got our olivines down here at the bottom of our chamber, our pyroxenes over here, and our amphiboles right there. Okay? Now let's make our calcium feldspar. Bet you'll never guess what's in that one. We're making magma chambers. You have a bowl of M&Ms and a magma chamber, so you can catch up pretty quick. All right, what's in our calcium feldspar?
Calcium.
Calcium, good. And aluminum, good. Those go down there, just right there with amphibole. By now, our magma chamber is really depleted in irons and magnesiums and highly enriched in silicons and the remaining light silicate building elements. So now we're going to make some potassium feldspar, which is going to end up right over here at the top of this area. Potassium, aluminum, and silicon. Okay, now we're going to make some biotite mica, which is a dark silicate. That's going to take up some more irons and magnesiums if you got them. Hopefully you still do, right? That's going to go down right here next to potassium feldspar. Cold. I actually like the cold. This isn't terribly cold for me. I was walking around outside just in this earlier this morning. One of my friends that works here called me legitimately insane. So, all right, are we ready? Next up, muscovite mica. 2 reds, 2 blues, and 6 silicons. M&M's down. His magma chamber just spilled everywhere. He had a volcanic eruption over there. Okay. It's a long one. I'll give you another second to catch up. All right. Now, someone tell me what's left in your magma chamber. There's some other. We'll talk about that in a minute. But you've got a lot of silicons left, right? And very few aluminum, iron. The ratio of iron and magnesium to everything else is significantly lower now than it was at the beginning, is it not? Okay. But we've got something else that needs to form. Quartz, 1 silicon. Because quartz is SiO2 and the oxygens are implied, right? So 1 silicon here. And now let's look at this. We have separated our magma chamber into our different composition categories based upon when these things form and therefore what minerals are going to collect with each other. Ultramafic is our olivines and our pyroxenes. Mafic includes some olivines and pyroxenes, but a lot of calcium feldspar and amphiboles. Intermediate, some amphiboles and calcium feldspars, but a lot of potassium feldspars and biotites. And felsic, some potassium feldspars and biotites, muscovites, quartz. And then finally, what's at the top? Pegmatite. And what's going to go in the pegmatite right there at the end of our magma chamber's life? Those two little brown M&Ms that you've got, those are labeled as other, all that rare stuff. When I say rare, think about what I'm talking about. 2 brown M&Ms in your entire bowl of M&Ms earlier. Nearly inconsequential, right? In the grand scheme of things. They don't want to bond with anything. They're cool to just hang out until now. Here we are at the end of the magma chamber. And those 2 M&Ms are now a significant quantity of your remaining chemicals. Are they not? And so they have to bond with something. And they do. And that's what makes our pegmatites right up there at the top, which are rich in those rare elements. Golds, silvers, platinums. We find these in pegmatites all the time. Lithium. AO. Lithium. We need that. Becoming rarer than gold almost. What do we use lithium for?
Batteries.
Rechargeable batteries. Lithium ion batteries. Okay. Okay. So here we have the differentiation sequence based on Bowen's reaction series using M&Ms. I hope that was fun for you. You may now proceed to devour your M&Ms if you wish. Okay. All right. So Bowen's reaction series can, in fact, experience a few shifts, a few changes. As while the sequence remains the same, it can be changed, or the order of some things can be changed. Let me explain why. Here we have our classic Bowen's reaction series differentiation, okay? Our new, nice, hot magma body. Things start to cool off. They start to settle. You start forming crystalline layers until finally where you had an ultramafic magma body to start with, now we have a felsic remaining magma chamber here that is feeding whatever outlet, aka volcano, is on top of it. However, some things can happen to affect this outcome, or at least the linear progression of this outcome. For example, what is our magma doing as it's making its way up from the mantle? Huh? It's cooling down, but what's happening as it's going up? Do you think it's saying, excuse me, pardon me, I just got to get through here to the rest of the rock around it? It's what? It's picking up and? What's it doing to the rock around it, do you think?
Either melting it or carrying it with it.
It's got to melt it. It's got to make room. It's got to make space to go up. And the rocks aren't really going to say, oh, yes, let me just part for you, right? It's got to melt its way up through the crust. And as it's melting its way up through the crust, whatever it's melting through is going to affect its composition, right? So you can melt things out of the host rock around it that will either progress Bowen's reaction series faster, aka increase the amount of light silicate content in your magma artificially, or make it take more time, or introduce totally different things, like way more calciums than it should have. There are a few rare circumstances where non-silicate volcanism happens. There's a place in Africa that I really want to go see with a name I cannot pronounce, but it is a mountain that has calcite lava. It looks like mud, but it's just as hot as normal lava. Like it looks like just a mud fountain, but you go up, you get anywhere near it, you're going to light on fire, right? Just like you would with normal lava. It is extremely hot, but it's made out of melted calcite, calcium-rich minerals, not your normal igneous minerals. It's fascinating. So there are a few exceptions based upon what our magma goes through on its way through up to the surface. Now, here's another example. What happens if I have a magma chamber that's gone partially through Bowen's reaction series? Let's say it's somewhere in the felsic category now. It's been around not long. And then a brand new ultramafic magma chamber on its way up encounters it, and they commingle. They intermingle with each other. What's going to happen? Huh? Say it louder. Sorry. Assimilation. Good. Intermingling. Assimilation. There are both those words work here. You go from having just a felsic and an ultramafic to they're going to combine and probably have a combined mafic composition. And the lifespan of this magma chamber in general has just been increased that much longer as well, because now it has to go all the way back to nearly the beginning of Bowen's reaction series. Okay. Okay. Now let's talk a little bit about that partial melting I mentioned earlier. Okay. Okay, now. Come on. Okay, partial melting. When I increase temperature and some things melt and other things don't. Let's show you this example here. Here I have 3 different substances. The first one, arcone on the left. This is linseed oil, very low melting point. Ice, melting point 0 degrees Celsius, right? Then the other one was chocolate. Come on. Okay, so we start to increase our temperature. What's going to happen? Our linseed oil starts melting almost immediately. Okay? Think of that as your quartz in your granite. It forms at low temperatures and melts at low temperatures. Then we get our ice. Think of that as kind of like your feldspar. Okay? It starts to melt. And then it takes a much higher temperature for us to start melting our chocolate. Okay? Think of that as more along the lines of your amphiboles or your pyroxenes in your granite. Okay? That's partial melting. When a body of magma pushes up through the crust, it intrudes on whatever was there before. Intrusive magma bodies have different names. We classify them based upon their shape and their relationship to the rock around them. We have massive and tabular intrusive igneous bodies. And then if the tabular ones cut along the host rock, we call it concordant. And if it cuts through the host rock, we'll call it discordant. So I'll show you some examples in a minute. But these large, massive bodies, we call these plutons, okay? And they, I'll show you some examples in a minute. I'll do the tabular ones first, I guess. I thought they were switched. I may have accidentally reversed which one I talk about first, but that's okay. We'll talk about the tabular ones first. Tabular ones are called dikes and sills. A dike is a tabular igneous intrusion that cuts perpendicular to the layers of rock that were there already. So if I have layer upon layer sedimentary rock piled on top of each other, remember our law of superposition that we talked about in our first week? Layer upon layer upon layer upon layer, oldest on bottom, youngest on top. But wait, now I have an igneous intrusion slicing perpendicular to those. Okay? That is a dike. A sill is the same thing, but instead of slicing perpendicular to those, it cuts horizontally through them, or I should say parallel to them. Okay? I'm trying to avoid the words horizontal and vertical for a good reason. Let's say that I have layers of rock like this. Okay? Got to put the right cap back on the right pen or it'll drive me nuts. And then I have an igneous intrusion that does this. Dike or sill? Dike, good. What if it does that? Sill, good. Now let's say that some tectonic shift has caused my layers of rock to be tilted vertically like that. And I have the same orientation here. What is this? Oh, but why? It's vertical. This one was vertical. Why is that one a dike and this one a sill? It has to do with its orientation to the host rock, not its orientation to our perspective. So even though that one's horizontal, it is a dike because it is cutting perpendicular to the layers of host rock. That's why I'm trying to avoid words like vertical and horizontal. Let's go with parallel and perpendicular. Okay. This is an example of a dike slicing through the layers of rock up there. And this is a sill that you're seeing exposed on the surface. That's Giant's Causeway over in Britain. Highly recommend a good visit. Okay, the massive bodies. So we just talked about the tabular ones. The massive ones, these are huge, okay? These will often form mountains or mountain ranges. A batholith, that's how you say it. I don't have a lisp. I know every time I say it, it sounds like I have a lisp. Batholith. Doesn't it sound like I have a lisp? Yes, no, it's a batholith. Is a massive intrusive body that is more than 100 square kilometers. And a stalk is the same thing, but is smaller than 100 square kilometers. That's surface exposure, okay? Or surface exposure plus whatever we can perceive in the immediate, yeah, of course. Okay, in the immediate underground area, okay? It could be very much larger underneath of that, but we can't classify that because we can't see it very well, okay? So just magma chamber basically that is exposed at the surface. It's been cooled off, it's been solidified, and now it's exposed at the surface because it's that old, it's been pushed up that far. When a magma chamber, while it is still liquid, causes dikes and sills, those tabular bodies, to split off to the side and start a secondary chamber somewhere else, you know, kind of shoving space, pushing the layers of rock above it up. This sort of secondary chamber, we call that a laccolith. So if I'm hiking up here and I'm like, huh, look at this cool stock. This is pretty cool. And it's like, I'm going to classify them. Like, oh, what's that over there? I hike over there and I find it's the exact same composition as that. I know that at some point, this kind of branched off and made a secondary chamber over here. So this would be my main stock and that would be my secondary, aka laccolith. Okay. Many of our mountain ranges on the west coast of the United States, everywhere that you see that's red here, these are either laccolith stocks or batholith mountains in those ranges. You're going to laugh every time I say that, aren't you? Yeah. All right. Now, a lot of this igneous material is very valuable for mining, especially those pegmatites. This pegmatites being so rare in those elements that we cannot really find in other places, at least not in the same richness, the same ore quality. You remember that word ore I used last week when we learned about mineral resources a little bit? An ore is a rock that possesses enough of a rare resource that we can mine it profitably. So we target batholiths, we target pegmatites all the time as mining sources. The gold mine that I used to work at, we would look for igneous plutons, identify where their pegmatites are / were, and if there was a pegmatite deposit, we would look for gold there. But sometimes what will happen is, as our magma chamber is cooling off near the surface, the groundwater, which is the water that moves through the different layers of rock around this structure, the groundwater would dissolve the gold out of the pegmatite and carry it through the groundwater flow somewhere else. So oftentimes what we would have to do is we would identify the area of departure. Where was that gold? And then we would have to, using drills, follow the path that that water took until we found where that gold ended up, where it reprecipitated. And then we would build a new mine on top of that location to target that gold deposit. That's called a hydrothermal deposit. Okay, but it's not just gold. We can find lithium, cesium, uranium, those rare earth elements that I mentioned earlier. These are all things that are necessary to maintain our level of technology as either conductors or various other electronics components like those rare earth elements are. So this is a very important part of geology to study because this is how we figure out where these elements form and where they could go next, where they did go next in some cases. Any questions about that? About anything at all today? All right, well, that's lecture then. No new lab today. You still have lab 1 assigned. You will get lab 2 on Thursday, the next time we meet. You have a question? Yes, you may. All right, I'm going to end the recording here. My online students, feel free to post any questions you have here or email me, and I'll get back to you.